Section 8.7, Exceptions to the Octet Rule. The octet rule is so simple and useful in introducing the basic concepts of bonding that you might assume it's always obeyed. In Section 8.2, however, we're noted the limitation in dealing with ionic compounds of transition metals. The octet also fails in many situations involved in covalent bonding. These exceptions to the octet rule are of three main types. 1. Molecules and polyatomic ions containing an odd number of electrons. 2. Molecules and polyatomic ions in which the atom has fewer than an octet of valence electrons. And 3. Molecules and polyatomic ions in which an atom has more than an octet of valence electrons. Odd numbers of electrons. In the vast majority of molecules and polyatomic ions, the total number of valence electrons is even, and complete pairing of electrons occurs. However, in a few molecules and polyatomic ions, such as chlorite, nitrogen oxide, nitrogen dioxide, and peroxide ion, the number of valence electrons is odd. Complete pairing of these electrons is impossible, and an octet around each atom cannot be achieved. For example, nitrogen oxide contains 5 plus 6 equals 11 valence electrons. The two most important Lewis structures for this molecule are less than an octet of valence electrons. A second type of exception occurs when there are fewer than 8 valence electrons around an atom in a molecule or polyatomic ion. This situation is also relatively rare, with the exception of hydrogen and helium, as we've already discussed, most often encountered in compounds of boron and beryllium. As an example, let's consider boron trifluoride. We'll follow the first 4 steps of the procedure at the beginning of Section 8.5 for drawing Lewis structures. We obtain the structure. There are only 6 electrons around the boron atom. In this Lewis structure, the formal charge on both boron and fluorine are 0. We could complete the octet around boron by forming a double bond. In doing so, we see that there are 3 equivalent resonance structures. The formal charges on each are shown in red. These Lewis structures force a fluorine atom to share additional electrons with a boron atom, which is inconsistent with the high electronegativity of fluorine. In fact, the formal charges tell us that this is an unfavorable situation. In each of the Lewis structures, the fluorine atom involved in the boron-fluorine double bond has a formal charge of positive 1, while the less electronegative boron atom has a formal charge of negative 1. Thus, in the Lewis structures in which there's a boron-fluorine double bond are less important than the ones in which there are fewer than an octet of valence electrons around the boron. We usually represent boron trifluoride solely by the leftmost resonance structure, in which there are only 6 valence electrons around boron. The chemical behavior of Bf3 is consistent with this representation. In particular, Bf3 reacts very energetically with molecules having an unshared pair of electrons that can be used to form a bond with boron. For example, boron trifluoride reacts with ammonia, NH3, to form the compound ammonium boron trifluoride. In this stable compound, boron has an octet of valence electrons, and we'll consider reactions of this type in more detail in Chapter 16 when we study Lewis acids and bases. More than an octet of valence electrons. The third and largest class of exceptions consists of molecules and polyatomic ions in which there are more than 8 electrons in the valence shell of atoms. When we draw the Lewis structure for phosphorus pentachloride, for example, we're forced to expand the valence shell and place 10 electrons around the central phosphorus atom. Other examples of molecules and ions with expanded valence shells are sulfur tetrafluoride, arsenic hexafluoride, and iodide tetrachloride. The corresponding molecules with the second period atom and the central atom, such as nitrogen pentachloride or oxygen tetrafluoride, do not exist. Let's look at why the expanded valence shells are observed only for elements in periods 3 and beyond in the periodic table. Elements of the second period have only 2s and 2p valence orbitals available for bonding. Because these orbitals can hold a maximum of 8 electrons, we never find more than an octet around the elements from the second period. Elements from the third period and beyond, however, have ns NP, and unfilled ND orbitals that can be used in bonding. For example, the orbital diagram for the valence shell of a phosphorus atom is 3s2, 3p3. Although the third period elements often satisfy the octet rule, as in phosphorus trichloride, they often exceed the octet by seeming to use their empty d orbitals to accommodate additional electrons. Size also plays an important role in determining whether an atom in a molecular or polyatomic ion can accommodate more than 8 electrons in its valence shell. The larger the central atom is, the larger the number of atoms that can surround it. The number of molecules and ions with expanded valence shells therefore increase with increasing size of the central atom. The size of the surrounding atoms is also important. Expanded valence shells occur most often when the central atom is bonded to the smallest and most electronegative atoms, such as fluorine, chlorine, and oxygen. At times, you may see Lewis structures written with an expanded valence shell, even though structures can be written with an octet. For example, considering the following Lewis structures for the phosphate ion PO4 3. The formal charge on the atoms is shown in red. In the Lewis structure shown on the left, the phosphorus atom obeys the octet rule. In the Lewis structure shown on the right, the phosphorus atom has an expanded valence shell of 5 electron pairs, leading to smaller charges on the atoms. Which Lewis structure is a better representative of the bonding in phosphate? Theoretical calculations based on quantum mechanics suggest that the structure on the left is the best single Lewis structure for the phosphate atom. In general, when choosing between alternative Lewis structures, if it's possible to draw a Lewis structure where the octet rule is satisfied without using multiple bonds, that structure will be preferred.